Okay, we finished up this quarter by talking about the initial aspects of thermal chemistry. Thermal chemistry is that idea around the heat produced or absorbed when a chemical reaction occurs. So first of all, let's get a little refresher course on energy in general. Energy is the ability or the capacity to supply heat or to do work. In physics, it's frequently defined as the ability to do work, which encompasses both of these aspects. Potential energy, and there's actually 8 different forms of energy that are frequently discussed. We'll not talk about all 8, but potential energy is part of what's known as mechanical energy, and it's the energy that an object has based on its relative position in space, condition, or composition. For example, this match here has a potential energy because it's made up of a combustible material that once lit will release heat energy. Kinetic energy is another form of mechanical energy that is the energy that an object has because of that it's in motion. Chemical energy is another form of energy, and it's actually quite important. First of all, on the left here under A, you see a cheeseburger. A cheeseburger is a form of food that we eat maybe for lunch, and it supplies us energy for our bodies to run for the remainder of the day. Gasoline, through its combustion, provides energy to move cars and people to and from work, school, home, etc. And then on the right here under C, you see coke, which is a processed form of coal, and it provides energy to iron ore to produce steel. A here shows another form of potential energy, and that form of potential energy is the falling of water off the waterfall. That falling of water can actually do something called work, and work is a force that's exerted over a distance, in this case falling from the top of the waterfall to the bottom of the waterfall, or it's a force that causes matter to move against a resistance. Water that has a higher potential energy falls off Victoria Falls here, and as it falls, it releases kinetic energy. Now, if it's on the right here in a hydroelectric power plant, that potential energy or kinetic energy can be harnessed and transferred through the turning of generators to form electrical energy. Now, just through these few slides, we've talked about potential energy, kinetic energy, chemical energy, and electrical energy. So there's 4 of the 8 forms of energy. Now, thermal energy, which is another form of energy, is the kinetic energy that is due to the random motion of molecules and or atoms within a substance. So if on the right you have cold water molecules are moving more slowly, and so they have less thermal energy than the hot water on the left. Temperature is the average kinetic energy of the atoms and molecules in a substance. So it's the total kinetic energy divided by the number of atoms or molecules in the substance, whereas the thermal energy of a particular substance is its total kinetic energy, not the average. You have to keep those two concepts straight. The thermal energy is the total kinetic energy of the atoms and molecules within a substance. The temperature is the average kinetic energy of the atoms and molecules within a substance. And those are 2 totally different things. Something can have a high temperature but actually have less thermal energy than something else if the second object is much larger than the first object. For example, a pot of boiling water has less thermal energy than a lake at 12 degrees centigrade, because the lake is much larger than the pot of water, but the temperature of the pot of water, the average kinetic energy, is higher than the average kinetic energy in the lake. The molecules of a sample of hot water move more rapidly than those in a sample of cold water. And this sort of thing is taken advantage of to measure temperature. And this is actually two different ways in which temperature is measured. Heat is the transfer of thermal energy from a warm object to a cold object. And it's frequently abbreviated lowercase q. So when we use the lowercase q, we're talking about the heat. A lowercase w is used to talk about work. So with thermometers as shown on the left, you can have a liquid such as alcohol or mercury within a glass or other type of solid tube, and the liquid will expand or contract more rapidly and more completely than the tube that it's contained in. And this expansion when it's heated up or contraction when it's cooled can be calibrated and allow you to measure the temperature. Now another way to measure the temperature is on the right here. You have a bimetallic strip, that is a strip in which one side is made of something such as brass and the other side is made of something such as steel. The two strips have a different coefficient of coefficient of expansion. So when one is heated, in this case the brass expands more rapidly than the steel and causes it to unwrap, and that can be measured. And when it cools, it wraps because the brass changes its length more rapidly than the steel does. And these two types of thermometers can be calibrated based on the substance that's used inside the glass tube or what metals are used for this bimetallic strip. Now you have two substances shown on A here. They have H is hot and L is cold, and they have different temperatures, and their atoms have different average kinetic energies. In B, they come in contact, and when they come in contact, there's a transfer of kinetic energy from H to L. And then ultimately, the kinetic energy becomes equalized between the two sides, H and L, and that's called thermal equilibrium, in which case all the molecules now have the same kinetic energy. This form of heat transfer is called conduction. Conduction occurs when heat is transferred due to direct contact between two substances. Reactions that occur, chemical reactions that occur, can either produce heat or they can absorb heat. If a chemical reaction produces heat, it's called an exothermic reaction. And that heat is considered a product of the reaction. And A represents a type of exothermic reaction. Conversely, a reaction that absorbs heat or requires heat in order to be completed, whereas heat is now a reactant as opposed to a product, is called an endothermic reaction. And this is shown B, where ammonium nitrate is dissolved in water. So A is an acetylene torch that produces heat by the combustion of acetylene with oxygen. The energy that's released in the combustion of acetylene and oxygen is an exothermic reaction, and it melts metal and causes a cutting of the metal. B is an endothermic process that creates a cold pack that can be put on injuries and so forth. Heat capacity is the quantity of heat that is added to any object or substance that causes it to change 1 degree centigrade. So heat capacity, capital C, is equal to Q over the change in temperature T, in which case the change in temperature is 1 degree centigrade. Now, specific heat capacity is the quantity of heat added to 1 gram of a substance to change its temperature 1 degree. So little c is the heat when the mass is controlled by 1 gram. Due to its larger mass, the frying pan on the right has a larger total heat capacity, so this is analogous to thermal energy, than the smaller frying pan. Because they're made of the same substance, they both frying pans have the same specific heat capacity, and in which case they would potentially both have, say, the same temperature, but have different thermal energies because they're different sizes. So that those two concepts are somewhat analogous. A calorie is the amount of heat required to raise 1 gram of water 1 degree centigrade. So, and usually this is what's known as a little case c calorie. A joule is the work performed. If you've had physics or even if you've had basic science, you might remember this, but a joule is the work performed to move 1 Newton of force 1 meter of distance. And that amount of work is equivalent to 4.2 joules of work is equivalent to 1 calorie of heat in terms of the transfer of a mechanical unit to a heat unit. So if you have a container that contains 25 grams of water at 25 degrees, how much heat would be required to raise the temperature to 82.5 degrees centigrade if the specific heat capacity of water is 1 calorie per gram per degree centigrade? Here's how we would do this problem. Q is going to equal to the mass times the specific heat times the change in temperature. In this case, it's 825 grams times the specific heat times the change in temperature, which is 82.5 minus 25. So 82.5 minus 25 is 57.5 times 825. Q is going to equal 47,437.5. Now let's look here. We've got 3 specific, 4, 3, 4, so it's 3. So 47,400 calories. Calorimetry is the process involved in determining the amount of heat involved in any physical or chemical process. A calorimeter is a device that's used to measure heat transfer in a physical or chemical process. Now, these definitions I'm going to tell you are extremely important to keep straight in your head. So make sure you pay attention to these definitions. A system is a substance or substances that is undergoing a physical or chemical change, whereas the surroundings is the rest of the universe that's not included in the system. And you, many times, have to define what you mean by the system that you're dealing with. In a calorimetric determination, either an exothermic process occurs and heat is negative, which means that the thermal energy is transferred from the system to its surroundings. So you're aware of heat being passed out of the system into the surroundings. It has a negative sign and it goes from system to surroundings, and it's shown on the left in A. An endothermic process, conversely, occurs when the heat has a positive sign, and it indicates that thermal energy moves from the surroundings into the system. Now that's why you have to keep the definition of system and surroundings straight, and you have to keep the signs of heat straight, because the sign has to be right in order to get the right answer from whether it's an endothermic or exothermic process.